welcome to another lecture in the course on 3G and 4G wireless mobile communication systems. Before we start today's lecture, let me just do a brief recap of what we did in the previous lecture. In the previous lecture, we started analyzing the bit error rate performance of wireless communication systems with multiple receive antennas, that is diversity present in the system. We said the SNR at the output of the maximal ratio combiner in a system, wireless communication system with multiple receive antennas is given by this expression, which is the receive SNR is norm H square P over sigma n square, where P is the power in the transmitted signal, sigma n squared is the noise power, norm H square is magnitude H1 square plus magnitude H2 square, so on and so forth until magnitude HL square, where L is the number of receive antennas and H is the feeding coefficient associated with that particular receive antenna, that is H1 is the feeding coefficient associated with receive antenna 1, H2 is the feeding coefficient associated with receive antenna 2, so on up till HL is the feeding coefficient associated with receive antenna L. Alright, and this can be succinctly represented as G times P over sigma n squared, where G is the norm of H square. We also said that the average bit error rate is given as the instantaneous bit error rate averaged over the distribution of the gain of this wireless channel with multiple receive antennas, that is simply Q of square root of SNR, square root of G times SNR multiplied by f of G, where f of G is the distribution probability density function of G, integrated from the limit 0 to infinity, that gives us the average bit error rate. We said this can be derived by the following expression that is shown in this slide. It is albeit a slightly complicated expression. We simplified this expression further and we said at high SNR this expression is given as, the expression for bit error rate is given as 2L minus 1 choose L or 2L minus 1 C L 1 over 2 power L 1 over SNR to the power of L, that is the bit error rate at high SNR with L receive antennas. As we can see, this bit error rate decreases as 1 over SNR to the power of L. Remember earlier in a wireless channel, it decreased only as 1 over SNR when you had a single receive antenna. Now, we are saying that when we have multiple receive antennas, this bit error rate decreases as a function of 1 over SNR to the power of L. Alright. And we did a simple example. We said when we have L equals 2 receive antennas, similar to what we did in the earlier cases, what is the SNR required to achieve a probability of bit error? 10 power minus 6, and we saw a surprising result that SNR is just 30 dB, around approximately 29 to 30 dB, which is 29 or 28 dB smaller than the SNR or the transmit power required to achieve bit error rate 10 power minus 6 in a wireless channel with a single receive antenna. So, adding one more receive antenna has resulted in a tremendous decrease of 28 dB in the required transmit power, which means as we again saw that the transmit power when we have two antennas PW2 is about 1000 times less than PW1, which means if PW1 is around 10 kilowatts, PW2 is only about 10 watts, it is about 1000 times less than. So, adding one more receive antenna has result in a 1000-fold reduction in the transmit power required to achieve the same bit error rate performance. And we saw this is primarily arising, and of course, one thing we saw that this is, since it results in such a significant reduction in the bit error rate, it is a critical technology in all 3G, 4G wireless technologies such as WCDMA, HSDPA, LTE, WiMAX. And we said one reason why this is happening is because as the number of receive antennas L is increasing, the bit error rate is decreasing as 1 over SNR to the power of L, that is with 2 antennas it is decreasing as 1 over SNR square, with 3 antennas it is decreasing as 1 over SNR cube, and so on and so forth. As the number of receive antennas is increasing, the rate of decrease is progressively increasing. And we saw the important reason here is essentially because we computed the probability of the multiple receive antenna channel being in deep fade, and we said that probability is 1 over SNR to the power of L. So, we said since the probability of the channel being in a deep fade is decreasing as we are adding multiple antennas, the bit error rate is correspondingly decreasing. And then we saw an intuitive reason for that, but I had to rush through it in the last lecture because we are coming towards the end of the lecture. So, let me repeat that again in today's lecture, so that you get a better idea of what is happening. So, let me just start today's lecture again with a brief description of what we did in the last lecture. So, we said the intuition. So, let us start with the intuition for lower bit error rate with multiple receive antennas. We said earlier I have a system with one transmit antenna, I had a transmitter with one transmit antenna, I had a receiver with one receive antenna. So, this is, we said it had a single link. The performance of the system is adverse if this single link is in a deep fade, and I said that probability that this single link is in a deep fade. So, this system performance is adverse when the link is in a deep fade. The probability of deep fade equals 1 over SNR. All right. So, in a single transmit antenna, single receive antenna wireless system, the performance is worse or the performance is severely degraded when that single link, the only link that is there, is in a deep fade. That occurs with a probability 1 over SNR. Let us look at a corresponding probability for now for a multiple antenna system with a multiple receive antenna system. So, let me draw, so let me write down here multiple RX antenna system with a multiple RX antenna system. There is a link between transmit antenna and each receive antenna, that is between transmit antenna and receive antenna 1, there is link 1, between transmit antenna receive antenna 2, there is link 2, so on so forth. Between transmit antenna and receive antenna L, there is link L. All right. Now, this channel is in a deep fade only if all the L links are in a deep fade, because look at this, if only link L1 is in a deep fade, then I can communicate through link L2, L3, so on up to link L. If two of the links are in deep fade, then I can communicate through the rest of the links. So, this system is in a deep fade only when, and let me write this clearly, all L links are in deep fade. That is, for this system to have a high bit error rate, link 1 has to be in a deep fade, link 2 has to be in a deep fade, and so on and so forth, link L has to be in a deep fade simultaneously. Now, let me denote with EI the event that link I is in a deep fade. So, E1 denotes the event that L1 is in a deep fade, E2 denotes the event that L2 is in a deep fade, so on and so forth until EL denotes the event that link L is in a deep fade. So, now what we are looking at, what we want to look at is probability E1 intersection probability of E2 intersection so on probability of EL. That is, the probability that all links are in a deep fade is nothing but the intersection of these individual events. However, we know that these links are independent, which means each of these event is independent from the other, which means the probability of this intersection of events is simply probability of E1 times probability of E2 times probability of EL. The probability of all the links being in a deep fade is simply the probability, the sub product of the individual probabilities, because these events are independent. So, this is probability of E1 times probability of T2, so on and so forth until probability of EL. Now, we know that probability of E1 is nothing but the probability that link 1 is in a deep fade, and that is 1 over SNR. Similarly, the probability that link 2 is in a deep fade is PE2, which is also 1 over SNR. So, as a net result, the probability that all L links are in deep fade is the product 1 over SNR L times, and that is equal to 1 over SNR to the power of L. So, this is essentially why your bit error rate is decreasing as a function of L. The intuitive reason is that compared to a single receive antenna wireless communication system, now you have L receive antennas, which means all the L links have to be in a deep fade for this system to be in a deep fade, which means it is the intersection of these independent events. Each event has a probability of 1 over SNR. The intersection of L events has a probability that is the product of these individual probabilities, which is 1 over SNR to the power of L. Hence, the probability of this channel being in a deep fade is 1 over SNR to the power of L. That is the reason the bit error rate is decreasing at the rate of 1 over SNR to the power of L. Hence, the probability of deep fade with L RX antennas is proportional to 1 over SNR to the power of L, and that is the reason you see that the bit error rate is decreasing as 1 over SNR to the power of L. So, that is essentially the intuitive reason why, as you keep adding more and more receive antennas, your bit error rate is decreasing at a faster and faster rate. Now, let us go into some more understanding of these multiple antenna systems, because as we said, multiple antenna systems are key technology in 3G and 4G wireless communication systems. They are a part of WCDMA, HSDPA, 4G systems, LTE and WiMAX. So, it is very important to have a thorough understanding of multiple antenna systems and especially of diversity. The system we considered had multiple receive antennas. So, my system that I considered had multiple RX antennas. Look at this, these are multiple RX, this has multiple receive antennas. Okay, so, I have multiple receive antennas in my system. These antennas are placed in space, that is, in space they are placed apart from each other. Alright, so, unlike in time or in frequency, these antennas they are placed in different spatial locations. Hence, this multiple antenna diversity is also known as spatial diversity. So, this multiple antenna diversity is also known as spatial, or in space spatial diversity. This multiple antenna diversity is also known as spatial diversity. All right. Now, so let me title this as spatial diversity. So, let me title this as spatial diversity. Now, in the previous analysis, we assumed one critical assumption. We assumed that each of these L channels are independent. So, there is one critical assumption in previous analysis. We assume that these L links are independent. We assume that E1, E2, EL, which are the fade events, are independent, which are the deep remember, this is a critical assumption in the previous analysis, that this events, deep fade events across the L receive antennas are independent. We said we have L links corresponding to the L receive antennas, and each of the channels across these antennas are independent. That is the result. We had the probability of the intersection as the product of the probability. So, the key assumption here is the independence of these channels. Now, it turns out that for these channels to be independent, the antennas have to be placed sufficiently far apart. So, for independence to hold, antennas have to be placed sufficiently far. So, for independence to hold, these receive antennas have to be placed sufficiently far apart. For instance, look at this, I have L receive antennas. If the receive antennas are close to one another, then the signal received at these different antennas are highly correlated. That is the reason the independence assumption does not hold. So, the antennas have to be placed sufficiently far apart, so that the received signals across these L receive antennas are independent. And how far apart? So, the immediate question is how far apart? So, how far apart should these receive antennas placed? The answer to that question is the antennas, the minimum spacing required is equal to lambda over 2, where lambda is the wavelength corresponding to that carrier frequency. Hence, let me write this over here, for independent channels across receive antennas, the spacing required, or the minimum spacing required, equals lambda over 2, where lambda equals wavelength of the carrier. Remember, this is a radio wave and we said the carrier frequency is fc. So, the wavelength is simply the velocity of the electromagnetic wave, which is c, speed of light, divided by fc. Hence, lambda can also be written as c over fc, and fc is nothing but the carrier frequency. So, lambda equals c over fc, fc is the carrier frequency, right. So, fc is carrier frequency, c equals speed of light. Let us do a simple example to understand this concept even better. So, I will start with a GSM system, again simple example. So, example, consider a GSM system. Consider a GSM system. We already know, and we have considered this several times before. We know that in GSM in India, the carrier frequency is fc equals 900 megahertz. Alright, the carrier frequency FC is 900 megahertz for GSM, that is the 2G wireless standard, the global system for mobile communications. Remember, we discussed this in our very first lecture. Now, the lambda GSM or the wavelength corresponding to this GSM is C over FC, which is 3 into 10 power 8 divided by 900 into 10 power 6. So, the lambda of this GSM radio waveform is nothing but C, which is 3 into 10 power 8 meters per second divided by FC, which is 900 into 10 power 6 hertz or per second, which is essentially, I will write down the answer here, which is essentially 33.33 centimeters. So, the lambda is 33.33 centimeters. Hence, the spacing between the antennas, between antennas equals lambda over 2 equals 33.33 over 2, which is 16.66 centimeter. Hence, the spacing between the antennas in a GSM system for independence to hold is 16.66 centimeters. Now, look at this figure, 16.66 centimeters. If you look at a normal phone, if you look at a normal cell phone, it is around 6 to 7 centimeters in dimension, around 6 to 7 centimeters. So, on a phone, in a GSM mobile phone, it is not possible to place multiple antennas, well, at least not possible to place multiple antennas for independent channels, because the spacing required is 16.66 centimeters, while the dimension of the phone is only around 7 to 8 centimeters, 6 to 7 centimeters, right. So, in a GSM phone, not possible to place. So, let me write this again here. This is not possible to place multiple antennas, because this is greater than the dimension, because the spacing is greater than the dimension. Now, let us consider a 3G or 4G system. Now, in a second example, let us consider a 3G/4G system, and let us compute and again ask the same question, what is the minimum spacing. So, 3G 4G system, what is the minimum antenna spacing required for diversity or independence of this? Remember, the keyword here is also minimum, that is, the spacing can be either at least this, or the greater the spacing between the antennas, the better it is. But what is the restriction here? The restriction here is that the device itself is fairly small. So, there is not much of a leeway in terms of how much the space between different antennas can be, because a mobile phone itself is around 6 to 7 centimeters. So, there is not much spacing that is possible between the antennas. So, let us look at the spacing in 3G 4G system. We know that the carrier frequency for a 3G system is 2.3 gigahertz for a 3G system, which means lambda equals 3 equals C over FC, which is again 3 into 10 power 8 divided by FC, which is 2.3 into 10 power 9, gigahertz is 10 power 9 hertz, which is equal to 13.04 centimeters. This is 13.04 centimeters, and lambda over 2 is 13.04 over 2, which is 6.5 centimeters, and this is also the minimum spacing that is required. So, we are saying in a 2G in a 3G/4G system, the carrier frequency is 2.3 gigahertz. So, the lambda wavelength is C over F C, which is 13.04 centimeters, which means the spacing required is lambda by 2, which is 6.5 centimeters, and this is comparable to the dimensions of the mobile phone. Hence, you can have multiple antennas on your mobile phone in a third generation or fourth generation mobile phone, and the reason precisely is this, because as the carrier frequency increases, the required antenna spacing decreases, the wavelength decreases, hence the antenna spacing decreases. Hence, it is possible to place multiple antennas on the phone. Hence, more importantly, it is possible to employ multiple receive antennas or receive diversity, thereby reducing the bit error rate in a 3G, 4G wireless system. So, that is another reason why receive antenna diversity is a key aspect of 3G, 4G wireless mobile communications. So, it is possible to place. So, possible to place multiple antennas on a 3G/4G. It is possible to place multiple antennas on a 3G/or 4G. All right. Therefore, extracting receive diversity and drastically reducing the bit error rate. Let us now move on to one other topic, which is the last topic in this module, which is diversity order. The last topic in this module is what is known as the diversity order. Let me just proceed with a brief discussion of this topic on diversity order. If the bit error rate, let the bit error rate of a wireless system be given as a probability as a function of SNR, as let the bit error rate of a wireless system be given as P of SNR. Remember, bit error rate is a function of SNR, and we are saying that the bit error rate is essentially PE of SNR. Alright, so the bit error rate decreases with respect to SNR as the function PE of SNR. Then let me define the diversity order. It is a slightly complicated expression, but very intuitive, as we are going to see. Let me formally define the diversity order. The diversity order D can be defined as D equals minus limit SNR tending to infinity, that is at high SNR, log PE of SNR divided by log of SNR. So, the diversity order D is defined as minus limit SNR tending to infinity, that is at high SNR, log P, the ratio of log of the bit error rate, that is log of PE of SNR to log of SNR. This is the formal definition of diversity order. It is a slightly complicated expression, but do not be fazed by it. I mean, do not be distracted by this. Is slightly complicated, but we will see this is a very intuitive definition, and this is approximately related to, let me give you a first intuitive reason. This is approximately related to the number of independent channels. So, this definition of diversity order gives me approximately, if I know the bit error rate function as a function of SNR, it gives me the approximate number of independent channels in the system, or it also tells me at what rate the bit error rate is decreasing with respect to SNR. Let's look at some simple examples to clarify this even further. Now, let me take an example. Let me consider the wireless communication system that is we considered initially with one transmit antenna and one receive antenna. So, let us consider a wireless system. Remember, now there are two kinds of wireless systems. One is a wireless system that we discussed in the beginning, which has only one transmit antenna, one receive antenna. Then the wireless system that we discussed later, which has one transmit antenna and multiple receive antennas. Now, I am saying I am going back to the original wireless system, which has only one receive antenna. Wireless system, one receive antenna, which means L equals 1. We saw the bit error rate or PE of bit error rate at high SNR. We saw the probability of bit error or the bit error rate function as a function. I am sorry, this is not BR, but this is rather SNR. We saw that PE of SNR is nothing but 1 over twice SNR. All right. We saw that the bit error rate decreases as 1 over twice SNR. Now, let us employ our diversity order definition. Hence, the diversity order D is given as minus limit SNR tending to infinity my log of P of BR, that is log of 1 over twice SNR divided by log of SNR. This can also be written as minus limit SNR tends to infinity, minus limit SNR tends to infinity minus log of SNR. Remember, log of 1 over 2 SNR is nothing but minus log of SNR minus log of 2 divided by log of SNR. I will now bring the minus sign inside. So, this becomes limit SNR tends to infinity 1, because the log of SNR over log of SNR is 1, plus log of 2 over log of SNR as limit SNR tends to infinity. Now, look at this, as SNR log of 2 is a constant, as SNR tends to infinity, log of SNR also tends to infinity. Hence, log of 2 over log of SNR tends to 0. This term here tends to 0 at high SNR, that is SNR tending to infinity, which means the diversity order D is limit SNR tending to infinity of 1 equals 1. So, diversity order of a wireless communication system with one receive antenna is 1. So, let me write this down clearly. Diversity order with one receive antenna equals 1. Okay. So, the diversity order with one receive antenna equals 1. The diversity order with one receive antenna equals 1. Now, let us see what is the corresponding diversity order with multiple receive antennas. And now also you can also make intuitive, it also makes intuitive sense that the number of independent channels with one receive antenna is just one, that is between the transmitter and the one receive antenna, the number of channels is 1. So, it is not surprising that the diversity order is 1, which is related to the number of independent channels. Now, let us look at what is the diversity order of a system with L receive antennas. So, diversity order of a system with L receive antennas. We said the probability of bit error decreases with L receive antennas decreases as probability of bit error is given as 2L minus 1 CL 1 over 2 to the power of L 1 over SNR to the power of L. This I can compute the diversity order now as D equals minus limit SNR tending to infinity log of 2L minus 1 CL 1 over 2 power L 1 over SNR to the power of L divided by log of SNR. So, diversity order is minus limit SNR tending to infinity log of 2L minus 1 CL into 1 over 2 power L into 1 over SNR power L divided by log of SNR. This can be simplified as follows. This is limit SNR tending to infinity, I will bring the minus sign inside, that is L log SNR. Log 1 over SNR to the power of L is nothing but minus L log SNR, bringing the minus sign inside, it is log L log SNR plus, or rather minus log 2L minus 1 CL into 1 over 2 power L divided by log of SNR equals limit SNR tending to infinity L minus some constant which is log of 2L minus 1 CL 1 over 2 power L log of SNR. Now, look at this, this is a constant over log of SNR similar to what we had previously. This tends to 0 as SNR tends to infinity. So, this tends to 0 as SNR tends to infinity, implying the diversity order D is nothing but L. Hence, diversity order equals L. And remember, this is also intuitive because we said that the number of in a system with L receive antennas, the number of independent channels is L. Now, even mathematically by our definition of diversity order, it is turning out to be that the diversity order is L, which means the number of independent channels is L. Hence, the diversity order of a system with multiple receive antennas or with L receive antennas is L. That is the reason why, as the number of antennas are increasing, you have diversity, which means more independent channels, which means your bit error rate decreases much faster. Now, let us compute the diversity order of a system that is not straightforward. Let us go back to the very first system that we encountered, that is the wire line communication system. So, diversity order, let us compute the diversity order of a wired or wireline communication system, we said that the bit error rate, remember the bit error rate of a wire line communication system as a function of SNR is PE of SNR, which is equal to, we said this is the Q function of square root of SNR, and we said this is also approximately equal to e power minus SNR over 2. We said the bit error rate of a communication system in which there is a wire between the transmitter and receiver, that is a wired or a wire line communication system, is Q of square root of SNR, and we said its bit error rate is very low because this function decreases exponentially in SNR, that is it is approximately e power minus SNR over 2, which means now let us compute the diversity order of this system. The diversity order, or let me just write it over here, the diversity order D equals minus limit SNR tends to infinity e power minus SNR over 2 divided by, or log of e power minus SNR over 2 divided by log of SNR, that is equal to minus limit SNR tends to infinity. Remember, log of e power minus SNR over 2, log of exponential is nothing but, log is the inverse of exponential. So, log of x is nothing but x. So, log of e power minus SNR over 2 is minus SNR over 2 divided by log of SNR. I will bring the minus sign inside, which means this becomes limit SNR tends to infinity, bring the half outside, half limit SNR tends to infinity, SNR divided by log of SNR. Now, look at this, as SNR tends to infinity, both SNR and log of SNR both tend to infinity, hence this is an indeterminate form. When I have an indeterminate form, we all know from basic analysis that we can use the L'Hopital's rule. So, I am using the L'Hopital's rule, which means the limit is essentially I differentiate the numerator, differentiate the denominator. So, the limit is half limit SNR tends to infinity, differentiate the numerator with respect to SNR, that is simply 1, differentiate the denominator with respect to SNR, that is log of SNR. So, that is 1 over SNR, which means this limit is also half limit SNR tends to infinity of 1 over SNR, which is simply SNR. Now, this limit SNR as SNR tends to infinity is nothing but infinity. So, in other words, this diversity order equals infinity. That is a surprising result. So, this shows that a wireline channel, this shows a very beautiful intuition. It shows what is the intuition? Wireline channel has diversity order equals infinity, implies it can be thought of, or it can be thought of as comprising of infinite number of independent now this is the main intuition. Similar to wireless system, wireline communication system as having multiple receive antennas, that is L receive antennas, I can think of a wired limb communication system as the limit of a wireless communication system as the number of receive antennas L tends to infinity, and that is the reason why the wireline communication system has such superior performance, because it can be thought of as a system having infinite number of independent links, which means a very small bit error rate which decreases exponentially. Let me just go back to the slide to show you what we had. We saw that for diversity order 1 we had a high bit error rate, diversity order 2 slightly lower, diversity order 4 lower, 8 lower, 20 even lower. As the diversity order keeps progressively increasing, we approach, and the limit we approach AWGN, which is simply the digital communication channel. So, when we go to approach the limit, we approach the limit of the digital communication channel as L as the diversity order progressively keeps increasing in the limit, we approach the AWGN channel, because we can think of a wired or a wireline communication channel as having infinite diversity order. So, this is the final intuition that I would like to convey in this section, which is essentially that the wireline channel can be thought of as comprising of an infinite number of independent links. That is the reason its bit error rate is significantly smaller. Right. So, now with this discussion we have completed the first module on diversity and fading wireless channel. So, this completes a first module on wireless communication system, fading and diversity. Let us do a brief recap of the concepts that we have learnt. We have learnt the concept of a fading wireless channel. We have learnt the concept of a fading wireless channel. We have learnt the concept of a relay, how to model this fading wireless channel, which is a relay fading channel. We have learnt the concept of bit error rate in both wireline, wired, and more importantly wireless relay fading wireless channel with one receive antenna. We also saw that this bit error rate is high, and we said that to combat this bit error rate, a key idea is fading. So, we learnt about diversity, to combat fading. We talked about the bit error rate performance, the BER performance with diversity. We said diversity is a key idea which results in a decrease of the bit error rate of a wireless communication system. We analyzed the bit error rate with the diversity. We said that the bit error rate decreases as 1 over SNR to the power of L, where L is the number of independent paths or the number of independent channels, number of independent receive antennas, and we also talked about some other concepts such as spatial diversity, what is the minimum number of receive antennas, what is the minimum antenna spacing required to achieve independence of the channels, that is we saw that the minimum spacing is lambda over 2. We talked about spatial diversity, and then we finally concluded with an important notion of diversity definition of diversity order. So, these are essentially the topics that we have covered in the topics covered in the first. So, these are essentially roughly around 7 topics we have covered in the first module, but these are extremely important topics because these lay a foundation for every technology, let us talk about like CDMA, OFDM, MIMO, 3G, 4G, whatever we talk about in the rest of the course, the concepts of fading, deep fade, relay fading channel, multiple receive diversity, bit error rate, so on and so forth. All these concepts play a very central role, very key role in the topics that we are going to discuss in the rest of this course. Hence, please again go through the material of this module to revise these concepts and get a clear and lucid understanding of the material that has been covered so far. All right. Now, let me go to the next module of this course, which is the module on the wireless channel. So, let me go to the next module. This module, you can get more information about the contents of this module by going to the website, but this module is essentially titled the wireless which is the second module. So, this module is titled wireless channel, in which we will be taking an in-depth look at the properties of the 3G, 4G wireless channel and asking and trying to understand more about the nature of this wireless channel and how specifically the wireless channel affects communication, affects 3G and 4G wireless mobile communication. So, we will understand how does the radio wireless channel, how does the RF radio frequency wireless channel affect 3G/4G wireless mobile how does the radio wireless channel affect 3G and 4G wireless mobile communication? What is the role of the wireless channel in 3G, 4G wireless mobile communication? Let me again start at a place which we are already familiar with. We said in the very beginning that we have a base station that is transmitting, all right. We have a base station that is transmitting to a mobile phone, all right. This is a base station this is a mobile station. We said in this scenario there is a direct line of sight path, but there are also many indirect non line of sight paths. So, let us say I have some trees, they act as scatterers which scatter the signal, and let us say I have some buildings over here, they act as another set of scatterers and they also scatter the received signal. So, this is a line of sight path, then there are several non line of sight paths, NLOS paths, which are arising due to the scatterer. So, there is line of sight equals line of sight, which is the direct path, and there are several non line of sight paths which arise due to scattering. Non line of sight paths which arise due to scattering and scatterers that are present in the environment. Hence, we said the net multipath channel or multipath wireless channel can be modeled as a delay, an attenuation corresponding to each of these paths and a delay corresponding to each of these paths. Each path, or we said the ith path, can be modeled as an attenuation AI and a delay which is given as an impulse delta t minus tau I, and I now sum across all the I paths I equals 0 to L minus 1, where L equals the number of paths AI is the attenuation of ith path, tau I equals the delay of ith path. So, each path has an attenuation A I, delay tau I. I am summing across all these L paths. I have L such multipath components. I am summing across the attenuation and delay components across all these multipath components to give the net channel, and this is H t, which is the channel impulse response. All right, L is number of paths or the number of multipath this is the number of paths, or in otherwise also the number of multipath components. Each component is characterized by an attenuation A I and delay tau I, and there are L such multipath components which are arising due to one direct path and a large number of scatterers in the mobile environment. So, this is what we already know. Let us start from here and this continue this module further to discover and understand, get a deeper understanding of the properties and the modeling of the wireless communication channel. So, I will conclude this lecture today with this discussion, and we will take it further in the next lecture. Thank you very much.